right? And then the integration over the supermodular will bring down appropriate terms in the correlation function. I think there is some. Yeah. Okay. And that in turn tells you what the correct insertion is.
And this, the two formulas, I mean, the two step which you gave, the product of chi's and then one removal of chi in the next step.
Yes.
This formula is the unique way of constructing, writing down the amplitudes with this.
Yeah, as far as I know, this is a unique way to write it. So it's independent of yeah. I mean, one way to derive it would be that imagine that you have chosen a coordinate system in which y is fixed. Okay. Now you are free to change your coordinate system in which y will start varying. Right? This is just a change of coordinates. And it better be that the initial formula that we had, where that term was not there, agrees with the final formula, where that term, so if you don't include that term, right, then you will find that the two things don't agree, right? Because from the integral over b, once you change the coordinate, those fs changes, right? Because the relation between sigma and tau will change, right, if you change in one patch. And because if fs changes, then the integral over b changes, right? And that picks up a residue from that location of the psi.
Because we define the picture changing operator, for instance, in a particular way, right?
Cube with psi, yes. Yeah.
And but is there any other way to define picture changing operator and then we could get a different formula for
you can always add to that, which is BRST exact.
But that
yes.
Won't change anything in amplitude.
That won't change anything in amplitude. Right? Again, as I said, I mean the way I introduced it looked ad hoc, but if you start from the supermodular integral, right, then you can see that this should happen. Right? Well, I mean, there are some things which you can reasonably easily see, that just like you have the that there should be a TF coming down, right? Because the gravity now should couple to TF, right? So that's part of the gamma TF, right? Gamma is needed because you want a 0 at the location of the puncture, right? So using those arguments, we can see already that this is a combination that you should have, right? At least pieces of this, right? And then you can ask how to complete this into a BRST invariant combination, right? And this is a unique way to do that. Any other question? Okay, so there is one point I noticed that in some places in my notes I had made a mistake in the notation. Right? So we had this del fs del ui or ti, right? Okay. And the fs, okay, at least this is how I had initially defined it, but then I changed the notation. So the fs is defined by sigma s being a function of tau s and the t's. Okay, the other use of the t's depending on whether you are in PGMN or MGMN. And when you write del fs del ti, this means that it is del fs tau s t del ti, okay, and this is at fixed tau s. Okay, it's clear that you cannot fix both tau s and sigma s, right? Because as you change t, right, either tau s changes or sigma s changes, right? This derivative is taken at fixed tau s. Okay. In some places in the notes, I had written sigma s in the argument, but that's not correct. It's sigma s you express as a function of tau s, and then you write this. Okay, is this okay? Okay, so today I'm going to write down a useful relation, and I'll indicate how it's proved, but not go through the details of the proof. We'll use PGMN. Okay, so you use a full fiber bundle to write down this relation. Okay, but a similar version also works in MGMN, just as by using pullback. So relation is the following. Okay, again, let me remind you that our notation is that these M NS vertex operators and N Ramon vertex operators. So the VIs are the NS vertex operators and WIs are the Ramon vertex operator. So this is given by -1 to the P Q is QB. Yeah. The BRST charge. Yeah, in the, from this viewpoint, BRST charge really acts as an exterior derivative. Okay, on these forms. Okay. So first, let's make sure that this thing makes sense. This is a P-1 form. If we take a D, it should be P of P form. Okay. And the idea is that that should be given by a sum of these. So this notation means, so -1 to the V. So -1 to the V is 1 if V is Grassmann even. And it's -1 if V is Grassmann odd. Yeah, close the bracket. Thank you. Okay, so the standard NS sector vertex operator shouldn't be. No, -1 to the V, right? Yeah, it's -1. So V, I'm not specifying what V is, right? V is this operator, right? If the operator is Grassmann even, then this factor is just 1, right? If it's Grassmann odd, then this factor is -1. Yeah. Okay. Is this notation clear? Right? So in NS sector, right, if you have the physical fields, for example, which have ghost number 2, right, one from left, one from right, then those are Grassmann even, right? So there will be no signs if those in the NS sector. Right? But in the NS sector, you may consider states which have ghost number 1, right, which are not the physical fields, right? But you may encounter cases where some of the vertex operators are ghost number 1. Okay? In that case, you will pick up a minus sign. Okay? And in the Ramon sector, it's opposite. Because there's an extra minus sign that comes because the Ramon sectors are supposed to be Grassmann odd from the space-time perspective. Right? So there, the ones which have host number 2 will pick up a minus sign. Okay, the ones which have host number 1 or 3 will not have a minus sign. Is this clear? Okay. So this sign we are thinking from the space-time perspective. In space-time. Yes, but if you pick the wrong host number, right? If we pick the wrong host number, then those actually are fermionic. Those are the host fields of cage fixing in space-time, from the space-time perspective, right? Which we didn't discuss from the string field theory perspective. Those Nebuchadnezzar states of wrong host number, right, are basically hosts and or anti-hosts. So which will have minus sign, right? Hosts are, even in the bosonic theory, the host fields have opposite statistics.
MS sector
is even and Ramon sector is odd.
The blues are the external insertions, right?
Exactly.
So we are not going to insert, I mean, okay, you might probably at some point, but we are going to insert on physical
Physical in the sense that they should be BRST invariant, right? But they could be pure gauge, for example, right? Or they could be physical but not doesn't have the correct host number, right? So there may be states of that kind. But this statement as I have given here, right, holds for unphysical states also. You don't have to demand Q invariance, right? This is a statement that is true for general operators.
I think we restrict ourselves to.
Yes, indeed, we will. Yeah. Yes, but nevertheless, this will be useful. Okay?
So the correlation, in definition of omega, there's a correlator, right? This B,
Yes. Yeah.
BV, W,
Exactly.
Chi's. If I take one of the V's or W's to be BRST exact, like QV,
Will be 0.
that correlator itself is 0.
We have to prove. We didn't prove
No,
it.
but then this omega P is.
What?
In this omega P, you have inserted QV1.
Yes.
Why is that not trivially?
Yeah, it will be 0. That will be 0.
That's how you prove like it is an field of omega.
Yeah, we want to eventually prove that result, right? We have not proven it. We are going to use this eventually to prove that.
But this is not zero in general, right?
Yeah, is it 0 in general or?
QV. No.
QV is not 0.
Omega p, any term in this.
Yeah.
Why is it not zero in general? Like
The way you are saying.
If you take all the V's to be physical.
okay, all of them is
Saying
physical,
don't take
then it
QV.
is
What?
Just saying take some arbitrary V.
Yes.
QV is still BRST exact by definition.
Yes.
So and insert it in the correlator. That
Yes.
CVV, QV,
Yes.
QV3. Is that 0?
No. No. No.
That is not
No. That is not 0 in general.
If
Right?
V was physical,
Amplitude will be 0. We have to want to prove it, right?
after integration and all.
After integration and all, amplitude, we have to prove that amplitude will be 0. Yeah. But correlation function certainly is not 0 in general. Is this statement clear? Okay. So I'll indicate how to prove this. And the general strategy is the following. Okay. You see, this can be thought of as a BRST contour integral around the vertex operator V1. Right? This one is a BRST contour integral around the vertex operator V2. Okay. And so on. Okay. These signs basically ensure that if you try to think of this as a combined chord, suppose you think of some of these two as a BRST contour integral around V1 and V2. Right? Then that BRST contour integral will take place at some point in the correlation function. Right? Now to take the contour to be around V2, you have to pass it through V1. Right? Imagine that you have something like this: integral JB of Z dz C V1 of Z1 V2 of Z2. Okay? And this C is around, this is Z1, this is Z2. This C is like this, right? Okay. So this I can write as a contour, I can just write it as a sum of the two contours. So this C is C1 plus C2. Yes, yes, you have to do this to start with. We want to write it this way. We have to relate this to this. Okay. So now, if we want to use the fact that this contour integral around C2 gives you, I used anti-clockwise, right? So let me put anti-clockwise. So suppose you want to use the fact that this contour integral is the contour integral of QB around JB around V2 of Z2, right? Then the JB position I have to change to here, right? During the change of the JB position, will pick up a -1 to the V1. Because this is BRS, this is Grassmann odd, right? So if this is Grassmann odd, it will become an extra minus sign. Right? It's that sign that is taken care of by these individual ones, right?
All these minus ones are just Grassmann parity of JB going through.
Exactly. All these minus signs are basically Grassmann parity of JB going through those vertex operators. Is this clear? Okay, if you don't like this, what we can say that you will just put some appropriate Grassmann odd or even numbers multiplying this vertex operator so that everything becomes Grassmann even. Right? Then these things will not be there. Okay? But eventually, then those Grassmann odd or even numbers you have to bring to one side, right? To be able to combine and get some identity, and that will pick up these minus signs. Okay, but it's not difficult to keep track of this minus sign. So basically, it's these are essentially the effect of QB passing through that the QB being rearranged to be next to a particular vertex operator. Okay. So then this sum on the right hand side can be thought of as a BRST contour integral around the whole all the vertex operators. Right? So if you have a contour that goes around all of these vertices. Okay.
Bypass going through a hole.
Yeah. So one can show that if you go through holes or handles, the way BRST invariance is intact. You can deform the BRST contour through holes and handles. Okay, because the boundary conditions are BRST invariant boundary conditions.
So any number of points on a Riemann surface of genus G, you will just cover with just a plane basically without no holes.
Yeah, exactly. You can cover the plane with this. Exactly. Right. This you can always do, right? But the non-trivial statement is that now, if we deform this, right, and if there are no other insertions anywhere, okay, then this integral can be shrunk to a point and give you 0. Right? That looks a little surprising, right? Because there are all these handles hanging around, right? How do you deform through those? Right? Yeah. The statement is that if you have something like this, okay, and as long as there is no other insertion in the correlation function, this and result is 0. Okay? Because this BRST contour, okay, can be deformed through these handles. Okay, even though it looks topologically impossible to deform the BRST contour through the handles, right? And that's because the way this is set up, the BRST contour actually can be deformed, right? Basically, the handles you can think of as summing over complete set of states in the middle, right? The way we defined it, right? And it basically amounts to passing the BRST operator through various identity operators.
If there is no, let's say, if there is no hole, then you can just, and there is no insertions also outside.
Then you can, on the sphere, you can always do it.
In between,
Exactly.
For a sphere,
Yeah.
it's trivial.
For sphere, it's trivial. The non-trivial statement is that you, even with the hole, you can. No. Topologically, it's not simple to imagine, right? Yeah, topologically, it's not simple to imagine. Of the BRST current, exactly. If you have a general contour, it's not true, right? It's a special property of conserved currents that you can do it.
If you write all the handles on the sphere.
All the?
Imagine all the handles as being this sum over R, sum over R.
Exactly.
Phi R, C, phi R, blah, blah. There is it easier to.
Yeah, there you can see that you can pass through. Exactly. Because phi R and phi RC have the same conserved charge, right? There is a conserved charge conservation, and using that, you can see that this is possible. Okay? But this is, I'm going to use it, I'm not going to prove it. Okay, that if you have a closed contour, right, on any genus Riemann surface, the contour can be deformed and shrunk to a point, even if there it looks like topologically there are these obstructions because of the handles.
What are the principles? This thing is there. This means like due to the signs, it is one integral over.
Yes.
Entire thing. Then the statement is that if it is on a sphere,
then it is 0. Yeah, I'm saying even if it's not on a sphere, you can still deform it to a point. The result will be 0. Right?
Sorry, but that's not true for any integral.
Any
Only
integral.
True with the JB insertion.
It's only true for
If it's conserved, the current, yeah, or any current, any conserved current. Right? If you have, for example, okay, you can say momentum conservation. put some e to the I k dot x's, right? And you want to prove the momentum conservation, right? You can do the same thing. You break integral del x mu product over I e to the I ki dot xi ki dot x of zi, right? This, when you put on each of these vertex operators, you will pick up a residue of ki, right? Okay, up to factors of I, etc. So this will be sum over I ki product over ki mu. Right? But we want to prove that this is 0. Because that's the momentum conservation, right? Even on hard genus surface. To prove that this is 0, you have to be able to deform this, right? And shrink it to a point. On the sphere, it's clear that you can do that, right? On hard genus surface, it's not so clear that you can do that. Right? But what I'm saying is that using the conservation laws, you can actually prove that it is possible to deform it and shrink it to a point.
Just that, like to deform it, to take it through a handle, I have to just put a contour, add a contour.
Yeah.
On that handle.
Exactly.
You contribution of that is somehow 0.
Exactly. So you add a contour, right? So you add one contour and opposite contour, and then the idea is that when you deform that contour, right, from the other side and bring it to the to next to it, right, it's still 0. They'll still cancel with a periodicity on the torus, right? Take a torus, right? You create one contour like this, one contour like this. The sum is clearly 0, right? They are next to each other. Now you can take one of those contours, keep one fixed, the one of those contours, go around that handle of the torus. Okay? So that should still be 0, right? Because they still cancel. Right? But in that process, this is a topology, you have spanned the surface of the torus. Right? So that's basically the idea. Okay, why you can shrink it to 0. Is this clear? No? Okay, let me try it. Take a torus with a point inside it, right? Here. We have a contour around here. Okay? So this contour I can write as a contour like it goes like this and it comes back like this. Sum of these two contours. Because when you collapse, right, the integrals cancel between all the other regions except around this point. Right? When you bring the two contours together, no, because there is a point, this point in between, right? So this point, you cannot make them coincide, but everywhere else you can cancel it, right? And you can do this. Now take this contour, okay, and this is a closed contour, so it's and there is no other insertion, so you can now take it to the other side, right? Pardon? You can. So I'm saying that because by under continuous deformation, right, this result, this integral will change only if you encounter a singularity. But there is no other singularity anywhere, right? So you can take this contour and go around, right? So then it becomes this is right? The same contour, except that instead of being on the right of this point, now it has come to the left of this point. But now they exactly cancel because there is no point in between. Right? So that is telling us that if you had a contour like this, right, the result is 0 because you can deform it to a point.
First step required.
The first step, just if you take the sum of these two contours, right, bring them together, you can deform them so that these two things will just coincide, right? What I'm saying, so for the first step required this. You think of the original contour as this.
Yeah, so that is like a disk around that plus.
But these two just cancel because they are the same integral running twice in opposite direction, right? So in this part, you are integrating g of z, right? Same function. One upwards, one downwards. Yeah, that's because you can deform the current. If it's not conserved current, right, the result between here and here will change. Right? Conserved is holomorphicity. Right? Del z bar of j of z equal to 0. Right? That's what you are using here.
If it was not holomorphic, it may have a similarity at the handle.
No, it will not be. If it's not holomorphic, then the result between these, this and this will be different, right? You cannot deform the contour.
Where is the handle posing a problem?
Handle is not posing a problem, right? I mean, you are using the fact that this thing is periodic around the handle, right? So that this result, right, by deforming it on the other side, okay, you are able to cancel it exactly. Yeah, it also holds for homogeneous surfaces. It's the same kind of argument.
This A cycle.
Hmm.
You just had that, no punctures. That is trivially 0
Yes.
for any holomorphic.
Yes.
Right?
Same argument, right?
There is no insertion in that.
There is no insertion in that case. You can just move or go around and make it 0.
Usually give that argument, collapse it to a
Oh,
similar.
if you just had if you just had a cycle, it's not trivial. If you had no insertion and if you just had took a
Which can just collapse to 0.
no, that is not 0. So you are not claiming that this thing is 0 by itself. Right? This plus this is 0.
Yeah.
Right?
We also, the fact that this thing is 0, then also means that this thing is 0. If you had a contour passing through the torus, not touching the function.
No, this thing is not 0. No. You cannot prove that this thing is 0.
But isn't the full contour, can't that contour be written as this contour plus this?
No. You can check that it's not homologically, it's trivial. This is new contour that you are using, right, is homologically trivial contour. It's not, a cycle contour is not homologically trivial.
Nonetheless.
No.
Then I don't understand what you are doing there.
Yeah, so what I am saying is that if we have a contour that can be shrunk to, that doesn't have anything outside, no other insertion outside. There are handles, but there also we had handles. No? If the contour is not wrapping a handle here, this contour is not wrapping a handle, right? So that's the difference. If the contour wraps a handle, then it cannot be shrunk to a point, right? If the contour doesn't wrap a handle, then it can be shrunk to a point. That's what we are using. Right? This is the example, right? That this doesn't wrap a handle, right? It cannot be obviously shrunk to a point, right? But it's as if it can be shrunk to a point by using this kind of manipulation. Yeah, if you have one more point, then it will pick up the residue from that point, right?
Both of them are inside this cycle, put a bigger
Then it will cancel. If you have 2 points, yeah.
No, this is not 0, right?
One is not 0 by itself.
No, then put one more thing and another round. That is not 0, right? If you have
No, that will be 0. If you put one, sum of these two will be 0. Because the sum, these two together, right, is like this.
minus sign.
You have to.
Here,
No, yeah, you can, this is again like this and this. You can make this to agree, right? Everywhere, so you can write this. If you have something like this, right? You can always write the contour, right? That one contour goes like this. The other contour goes like this. The opposite contour goes in the opposite direction. Maybe I draw a different chalk, colored chalk. Yeah. And then this part is the same. Right? So these two don't cancel, obviously. But once you go around the torus, right, then this contour will come to the other side, right? Then they cancel.
You're saying you have to take into account what function you have, like Grassmann order.
That you have to, that minus sign you have to do, right?
That minus sign you have to take. Yeah, exactly. That minus sign allows you to write this as one single contour integral, that one JB, right? To the left of everything that is there. Okay, so let's now see how to prove this. So the reason that this is not zero, the right hand side, we choose it to because we want to it to represent this, right? So the original contour should be deformable into sum of contours around each of these, right? Yeah. Exactly. Exactly. Right. The original contour we take to be just around these points. Okay. So the reason that it is not zero is because we have other insertions, right? The BIs. Remember, the actual omega contains the products of the vertex of powers and the BIs, right? So because of those BIs, the curly BIs, right? Because of those curly BIs, you will pick up residues from those positions, right? So we pick factors of QB with curly BI. But those are invariant, right? The chi's are QB invariant. So picture changing operators don't have any problem, right? It's the BIs which can cause possible obstruction. Pardon? Yeah, those are QB closed, exactly.
BIs were inserted where exactly? They were on the contour.
On the contours, right? So if you
Integrated.
some integrated object, which is okay, it's not a big problem, right? QB has to be passed through those. Now, in omega p, there are PBIs, right? There are PBIs, right? Basically, all of them give the same result, right? Because each BI is the same, right? So basically, what it does is that it takes this 1 over p factorial and multiplies by p, right? And then you can just focus on one QBBI factor. Okay, rest remains as b, right? One becomes QBBI, right? So what you get at the end is that you get QB BI and product J not equal to I BI.
Because the minus sign.
Yeah, I'll not worry about the minus signs, etc. Right? Those will all go into this minus 1 to the AP. Okay, these you have to figure out how to prove, right? But roughly it's like this. Okay? So you have to calculate this object, right, and see what it is doing. So now I'll write an expression for BI again. So BI was
Again, all my contours are inside the CIs.
Inside the
Yeah.
CS, yeah.
Yeah.
Yeah, on CS, yeah. Exactly.
It's inside, the JB contours are inside.
Yes.
And now I'm taking that out to get a full contour. I'm deforming all
Exactly,
to
exactly.
add them, and that's why I pick up that.
Exactly. That's right. Right? Because if without any insertion, you know that you can get the result, right? With insertion, you have to get extra, you will pick up extra residues, right? That's all we are saying. BJ, thank you.
Hi,
Yes.
can you hear me? I couldn't follow what's happening. So you gave this particular identity, the one you have written, and then you made a comment that if you have a contour where you have insertion and there is nothing outside these insertion, then you can shrink it to 0.
Yes.
And now what are you trying to prove using
Yeah.
using
So now
this?
you are saying that if there are things outside the insertion, then you will pick up residues from those,
Yes.
right? And the string amplitudes do have things outside the insertions, which are the BIs.
Yeah.
Okay. So you'll pick up residues from the BIs.
Yeah.
That residue is proportional for a given BI, the residue is proportional to the anti-commutator of QB with BI.
Yes.
And then I said that if there are P of those BIs, right? But each of those give the same result. Because all the BIs are the same. So you can just multiply this whole thing by a factor of P.
Yeah.
And in the definition of the omega P, there is a 1 over P factorial. So it basically converts the 1 over P factorial to 1 over P minus 1 factorial. And then you have this factor.
Yeah.
And now we are going to analyze this factor, what it is doing.
Okay. Okay.
Okay, because you want to prove that this factor is responsible for why we get d omega P minus 1 on the left hand side.
Okay. Okay.
Pardon?
The fact that you had omega P minus 1.
I had omega P on this side. This I started by analyzing this side. Yeah.
So you have P minus 1 B's and you have some dt1 dt, d1 d2 or whatever. And then you apply this d. It's like putting in an extra b.
This one has an extra b. No, omega P by definition has PBs, right? Yeah, I want to go from here to there. Then you can reverse the proof. Right? No, it will not be very hard. Right? I mean, let's go from the right hand side to left hand side, then you can reverse it.
So you're saying right hand side is just this contour integral.
Exactly. I deformed the contour, right? In that process, I destroyed one B, okay, into this, and there are P minus 1 B's, right? So these things are exactly what will appear, what should enter the definition of omega P minus 1, right? If it was not for the B, it will be just 0. Yeah, for 0 forms, it will be 0. Exactly, because minus 1 form is not there, right? So if P was 0 on this side, right? Yeah, RH is trivial 0, LHS doesn't exist.
But it should have been omega P minus 1.
But omega minus 1 is 0, right? So this identity for... Yeah. It should be dp minus 1, d omega p minus 1. We have to see why this is the case. Right? What he just discussed is a special case when p is 0, right? Because there's no b insertion. And the argument that I gave earlier says that this should be 0.
B insertions is P, right?
Is P. So if P is 0, okay, then there's no insertion, right? Then the right hand side is identically 0.
So that side.
Yeah, that doesn't exist. So that side is also 0. Yeah. So now we are talking about arbitrary P. Right? And you want to see what happens for arbitrary P. Is clear? Okay. So B was integral Cs d sigma s d sigma s Ti are the coordinates of this PGMN, right, which includes the moduli as well as the positions of the picture changing operators. So Ti's are these extended coordinates in extended space.
Some extension of the dipolar space with some super.
Exactly. It's not super. I mean, we are working still in the bosonic version. We integrated out the gravitinos, right? But the locations of the picture changing operators are arbitrary coordinate, arbitrary. Right? So those you are thinking of fiber. Right? And a particular choice of picture changing operator will correspond to a particular choice of section, because you have to specify the y alphas as a function of the base coordinates. Okay, again, this 1 over chi is fake because this will cancel against one of the chi's that are in the product. So if we take QB with BI, right? This B will be replaced by T, because Q with B is T, the energy momentum tensor. Second one should be Fs bar. Yes, thank you. T is real modulus, so you don't do anything there. So your C integral.
What is this third term? This third term wasn't there in the bosonic string.
Yeah, so this is the extra term that you have to add for superstrings. If the xi's depend on the moduli, then the third term is extra. And we will see why it's needed. If we call this by vector, because multiplicities it can depend on. Okay, here I have used the fact that QB with xi is chi. With chi, the picture changing operator. Okay, so this would have given del of chi. Yeah, the last term would have given del of chi here. And del of chi times del y alpha del Ti is just T derivative of chi. Okay, the dependence comes because the argument depends on T. Now the claim is that this object is minus del Ti of the correlation function, where you have the product J not equal to I, Pi product over Vi product over Wi, and chi. Pardon? Yeah, this is anti-commutative. Thank you. No, this is.
Equality is not the upper line. Yeah, it's
The-
not VI. It's not
No. Equality is that this after you insert into the correlation function. The rest of the B's are there, right? Okay, so it's not equal. Okay. So the RHS. Right hand side, right? Even then, it's not quite the case because you have to put the dt's, right? Which I have not done, right? So let me write dti1 to dtij. I think the way I had labeled this, was this product bi1 to ip, right? So bik, and this should have been til, and this is k not equal to l, something like that.
Yeah, but k going from 1 to
K going from 1 to p, yeah. So k equal to 1 to p, but without the LF term. Okay, so I have to explain why this is the case. Okay, why these insertions of this, right? So basically what is happening is that one of the BIs is getting replaced by this side, right? Okay, so that's why one of the BIs is missing, that is clear. That what you are saying is that in the original thing there are a product of P BIs. Now one of the BIs is getting replaced by this right hand side. Okay. Now I'm claiming that that object is the TI derivative of the one without one BI. Right? That's this one. Right? One BI has gone away, right? The fact that one BI would have gone away, that's clear because one BI has been converted to the right hand side. Okay. Why is it TI derivative is not completely clear, right? That's what you have to explain, right? Why is the TI derivative? Yeah, IL, it's summed over. Yeah, it's a repeated index, so it's summed over. Inside the D, yeah. Okay. So the reason that it's a TI derivative, right, is the following. So let's say where are the TI dependencies coming from? Right? One source of TI dependence is that the FSs depend on TI. Right? So when you change TI, the FS will change. Right? So FS changing means that the relationship between the sigmas and tau s is changing. Right? But that change we know is that this is change of coordinates. Right? And change of coordinates is generated by energy momentum. Right? Okay. So this is a qualitative argument. You have to, do it carefully to see that these terms, right, that we are seeing is essentially due to the change of Fs, right, the TI dependence of the Fs. Okay, this insertion essentially produces the TI dependent, that derivative with respect to TI due to the fact that Fs depends on TI. Del TI acts on what other things? Chi, exactly. That's this one, the third term. Right? This term is, so if all the FSs are fixed, right, and you change chi, the position of y alpha, right, clearly those terms will not see it, right, because there's an explicit change in y alpha coordinate. Right? It's not coming from a change of coordinate system. Right? You have just moved the y alpha explicitly. So that is captured by this one. This chi y alpha is multiplied by one of the chi y alphas, right? So that goes away. Right? So this is explicit derivative with respect to TI of the fact that the chi, there are TI dependence because chi depends on TI.
One is coming from the coordinate change, which is just t terms, right? The coefficient of t term.
Exactly.
And the one which is coming from the location change.
Exactly. Location change or picture change operator.
But how do we decide the sign?
So sign I will not do. You have to do it. Right? So you have to figure out that the particular combination of sign that is there, right, is exactly what you get. Okay. So the idea is that this is basically omega p minus 1, right? Okay, without the TIL term from here, this is omega p minus 1. Right? And you are taking the derivative of that and multiplying by dTIL. Right? That's exactly the exterior derivative operation. Right? Exterior derivative is our form is dTi del Ti of the original form, right? Yeah. So minus signs are up to you. you have to fix it, right? So basically, what you have to show, basically what happens is the dt lands up on the wrong side, so you have to pass it through all the dt's, right? When you use the definition of the exterior derivative within the, because in this definition, the dt, the extra dt that comes because of the exterior derivative is on the extreme right, left, right? Okay, they are basically it ends up at the extreme right, and so you have to pass it through, and that picks up this extra sign. Okay, so the -1 to the p basically comes from there.
Here 1b is 1, that's okay, then it's p minus 1.
Exactly, right? 1b is less, that's why it's p minus 1.
What is happening here is, so we start from RHS.
Yes,
We have all this QB acting on this insertion points.
yes,
We cross each disk and we shrink that to 0.
exactly.
So we get negative of these terms.
Yes,
Negative of these terms. Negative or maybe positive.
yeah, yeah, yeah. So sign you have to again figure out,
Yeah.
right? Negative or
So
positive, yeah.
We get sum of these terms, right?
Yes, right?
QBBI.
Exactly. So only one QBBI is needed because all the QBBIs are give the same result, right?
Right.
So that's what made that 1 over p factorial into 1 over p minus 1 factorial.
What was that 1 by p factorial?
Because omega p definition had a 1 over p factorial. Yeah,
And p we are getting because we have choices.
exactly. Because you have PBIs, right? So that p combines with this 1 over p factorial to make it into 1 over p minus 1 factorial.
That probably will go into the definition.
Yeah, that will go into definition of omega p minus 1.
Plasman even.
Pardon?
Right? Plasman.
Yeah, it's just one even. Yes. T. Right, that is crucial. That's the reason why you need B. Exactly. Yeah. Okay, but in the bosonic case, there is no extra data, right? So no analog of the chi's. So the T derivative comes only from the transition functions. No, you can't realize it. So you need the xi phi system. Right? If you want to generalize G amplitude, I think you do need the xi phi system. Chi host number is 0. Chi has all quantum number 0. Size host number is -1. You can assign. Because psi comes from beta, right? Beta is del xi to the minus phi. Yeah, all three comes as the same host number. No, you can. Delta beta, delta gamma, you can use, right? But that's the same as eta. Right? We are not using xi anywhere, right? So far, you have not used xi anywhere. Always del xi, right?
Now this is the term we have to add.
Yes, exactly. Meaning, if okay, somebody can say, okay, how do you know there is no other term, right? But at least this term, why this is needed is clear. Okay, because if the y's depend on t, right, then the explicit t derivative, right, from the y's, you have to cancel. Is clear? Okay, so now we'll see how it helps. Right? What can you do? We'll just prove two results using this. After
Hi.
boundary terms, which will be discussed next week.
Hello.
Yes.
Yeah, in the last equation that you have written, the RHS equal to that.
Yes.
So in that equation, when we are going to take derivative with respect to the TL, we will take derivative, the only non-zero, this will only hit with the picture changing operator, the Y alpha, it will rest.
Explicit dependence on TL, but there is also a dependence to Fs, right?
Yeah.
So you have to take into account the fact that the Fs, the T derivative will also act on the Fs. Right? And that will produce these other two terms.
Okay.
The first two terms.
Okay. Okay.
Right? And there you are using the fact that the energy momentum tensor is a generator of coordinate transform.
Okay, thanks.
Okay. So suppose and V1 is QB on some V0. Okay, V1 is BRSA trivial. And we want to calculate the amplitude. Over a section of QB0. Okay, so we are trying to calculate an amplitude where all states are physical and one of them is BRST exact. So now apply this formula, right? QB V0, right? The first one has Q something, this term is what we have here. All the other terms are 0 because V2 to WM are all BRST closed, right? Q on those are 0. So then this itself will be given by integral d omega dmn P, that is 1 in this case because P is even. Okay? This thing is even, so you don't have to worry about it. Here, V2 to Wn are physical. V0 is not, it's not physical. V0 is, if V0 is physical, then Q on V0 will be 0 anyway, right? V0 is arbitrary. Nevertheless, this formula is supposed to be valid for arbitrary V's and W's. Because Q on V2 is 0, because V2 is physical, right? V2 to WM are all physical states, right? So they are BRST closed, right? The first one we are taking to be BRST trivial. So this is a total derivative, right? Integral of a total derivative on the section. So this is 0 up to boundary terms. So as I said, boundary terms we'll discuss next time, because to discuss boundary terms, you have to know what the boundaries are, right? So which I have not discussed so far, so which we'll do, right? But up to boundary terms, we see that pure gauge states decouple from the amplitude. Is clear? Now, second result. So let me give this picture of the fiber bundle PGMN. So this is the moduli space, the base, and the fiber is the choice of picture change, right? The Y alphas. And a given amplitude requires a choice of section. This is our SGMN. Okay. And let's suppose that you have another section, S prime GMN, which is a different choice of picture change. Okay, and you want to prove that the integral along the final amplitude doesn't depend on whether this you use this or this. Okay, so integral over SGMN minus integral over S prime GMN. So you can write SGMN minus S prime GMN equal to a boundary term, a boundary of R GMN, if S GMN and S prime GMN coincide at the boundary. Pardon? RGMN is this, not a full space, one dimension higher, right? RGMN is not, so there are many choices of RGMN in general, right? It's like in 3 dimensions, you have 2 lines, right? There are many 2-dimensional surfaces that you can draw whose boundaries at those 2 lines, right? So RGMN is not unique, take any RGMN that you like. Okay. So the only danger is that these 2 things, if they don't coincide at the boundary, then there will be some extra terms from the boundary, right? Because then the tail of the boundary of RGMN will also contain those boundaries. Okay, but again, we will ignore those, right? Because those will be discussed later.
There can't be a hole in between them.
Yeah, the point is that we will see that there can be holes in between when we discuss these spurious singularities, right? But at this stage, this space, this fiber is trivial, right? It's just the location of the Y alphas, right? So there you don't really have a hole, so you just take this difference. Pardon? You can have intersecting, yeah. That's not a problem. Yeah, so RGMN maybe in some places you have to add, in some places you have to subtract, right?
RGMN is simply connected.
Right now we are pretending it's simply connected. We will see that later on, even if it's not simply connected, it doesn't really matter. It's effectively simply connected. Exactly, yeah. Well, even here, suppose one Y alphas, right, are such that as you change the moduli, right, on the Riemann surface, it just spans a trivial cycle. Another section, as you span the moduli, right, closed curve in the moduli space, then the Y's on the Riemann surface may go around a non-trivial cycle, right? In that case, it's not trivial, that, but we will see that, I mean, when we discuss this spurious singularities and particle integration, that even that doesn't matter. Okay, you can pretend as if it's non-singular. And this is basically has to do with the fact that the integral of del xi along a closed cycle is 0. Okay, but we will come to that later. Right now, let's just pretend that it's simply connected. Okay. So in this case, if you take the difference, that integral SGMN of omega GMN minus this is given by integral the Stokes law. Sorry, yeah. And there is plus 1. No, this is fine. Yeah, this is fine. Because this difference is Taylor, right, boundary of R, but we are using Stokes theorem, right? So we integrate over R and it's d omega. Is clear? Minus sign? No. S minus S prime I have declared as the boundary, right? So the integral over R is integral over the boundary. No, integral over dr is typical integral of the boundary, right? That's how we define R is a bulk, yes. There is a, in this case, no, there is a plus one. Or D. D makes it into a plus one form, right? No?
Previously you were writing minus one and no, I think the notation was of d omega.
Yeah, it's that should be the dimension of like
The d omega.
or the degree of omega, not d omega.
Yeah. Over here, for example.
Which one?
No, there it should be correct.
No, right.
E of something minus one.
Yeah, that's fine.
No. So it's you have to have a one form. This is a certain form, right? Let's call this P. Okay. Now this is a one-dimensional higher space. Okay. You have to have a 1 P plus 1 form, right? Yeah. So d omega is a P plus 1 form. Yeah. Now we are going to use the formula, right? So this is, yeah, we have not used the identity. This is just Stokes theorem, right? Now we are going to use the identity, right? That this is integral RGMN. Probably now there's a minus sign, right? But doesn't matter actually. Up plus minus GMN. Pardon? It's probably minus, yeah. But there is a odd form here, right? Yeah, because this is odd. It's clear, I'm just using that formula. But all of these are 0. Because V1 to Wn are physical states. Right? You are studying properties of a physical amplitude. Right? So this is 0 if V1 to Wm are physical. Okay, and here by physical I really mean BRST closed. Wn. Yeah, Wn. This is n, yeah, Wn minus 1 Wn. Then it is 0. Shouldn't it be which omega? D? No. D has gone because I am using that identity. Right? So you remove the D and replace it by Q. Action of Q one at a time, right? But each such term is 0 because as long as the states are physical. Okay? So this is basically showing that the integral of what the physical, that for physical states, it doesn't matter what section you choose, you always get the same answer. Not for unphysical states. Is this clear?
As long as the sections coincide in the boundary.
As long as the sections coincide at the boundary. Okay, or you have to show that the boundary terms are 0. On shell, yes. But on shell doesn't necessarily mean the k square is 0 because q on anything is physical, right? It's just because q square is 0, you can add q on anything. Right? So on shell doesn't necessarily mean that you have to that it has to have this particular form of CC bar V with L0 equal to 0. Is clear?
If you have unphysical vertex operators or unphysical states, then you have to be careful what section are you choosing.
Yes.
When there is no, is there a canonical choice for them?
No, there is no canonical choice. That's why in string field theory, right, where you deal with off-shell vortex operators, there are many choices. Each of them give apparently different string field theories, but what you can show is that those are all related by field definition.
In gauge theory, that if you the gauge, and if you're computing gauge non-invariant correlation functions, that depends on the section.
Exactly. Yeah, exactly. Right? Except that in this case, that in string field theory at least, the choice of section is not thought of as a choice of gauge, but it's apparently different string field theory because the action itself or the gauge invariant action depends on the choice of section. Right? But what you can show is that if they are using the same identity, that if you change section, right, that is equivalent to making a redefinition of fields in the string field theory action. Yeah, the two string field theories that are related by change of section are related by field redefinition. Yes. Yeah, it will be formalism. Batal Falkovsky formalism. No, you have. Except that the action, right, has to be constructed as an expansion. We don't have a closed form for the action.
So there you can see this field redefinition.
Yes. You can construct the explicit field redefinition that takes you from one section to another section. Yes, you can construct it. Right? The way you do it is you make infinitesimal deformation and you find infinitesimal field redefinition, which relates the two.
Transformation section first.
Yes. Okay. Transform the change the section by infinitesimal amount, and that you can show is related by field redefinition. In fact, I mean, you need more data for string field theory because for off-shell vortex operators, right, even the coordinate system that you use, the W's, matter. Right? So the string field theory action depends also on that data, what W you have chosen. Right? If you change W to some other coordinate system, let's say change W1 to W1 plus W1 square. Right? That will give again apparently different string field theory action. But again, what one can show is that that change also is a field redefinition of the string fields. Yeah, you can say the string field theory is redundant because it has a lot of extra data, right?
Not string field, world sheet. This is what we are doing in world sheet.
Yeah, world sheet, the point is it doesn't depend on that extra data, right? If you use the physical vortex operators, right? In that sense, string field theory has redundant data, right? Because it and that any quantum field theory will have redundant data, right? Because even Young-Mills theory, you can make arbitrary change of variables, right? And write the Young-Mills theory in that variable. Okay? That's equivalent to the original Young-Mills theory, but its action looks different. Okay? The same is true in string field theory, right? There is a lot of redundant data, but it's also useful sometimes because for some purpose, some choice of picture changing operator may be useful, right? Or some choice of coordinate system may be useful. For some other purpose, another choice of coordinate system may be useful. Right? So it is it's redundant, but it can also be useful.
Couplings are also involved.
That also is field, right? So you don't really have separate coupling. So field redefinition basically means you change some psi to some function of psi.
But I mean, this statement is surprising that you have the field redefinition to go from one to the other. Because in quantum field theory, I give you two field theories which are field redefinition cousins of each other. It's very difficult to say one is the other unless you do an explicit computation of the S matrix or something, right? Or is it possible?
Yeah, or you find a field redefinition explicitly. Right? See, even in string field theory, of course, there are many other field redefinitions which are not generated by either change of picture changing operator or change of coordinate system, right? But I mean, these are special ones, the ones that are induced by these transformations.
Here also go the other way. We deform the section, then we see what that means.
Exactly. Exactly. What field redefinition?
There is some redefinition, then we may not be able to.
Exactly. Yeah. Exactly. Yeah. Right. So only these. So these give one very special field redefinition of string field action. Okay, I think I'll stop here and then we'll continue next time.